This is, well, first of all, who am I? I work for Simply Business, which is, we have 290,000 policy holders for business insurance in the UK. So we're quite a large insurance provider. On our development and tech team, 45 people and about 60 people developing products on an ongoing basis, and about 100,000 lines of code increasing rapidly. And sort of how I came into this topic of technical debt bankruptcy was that we had a new shareholder that came in. By the way, this is not the mathematical part, so just sit tight, the exciting part is coming. We had a new shareholder. They were quite non-technical, and we had quite a difficult job explaining that after that we were replacing a 5-year-old system, and it was taking us 2 years, and actually 2 years probably wasn't replacing everything yet, but we had to do it. And the reason we had to do it was we simply could not economically make changes to that system anymore that allowed us to bring the business forward. And so that, I guess that just really made me wonder what is going on. Our product was locked in concrete. We had this. Has anyone heard of the concept of technical debt, first of all? That's a concept that's out there. One person. Oh, no, a few more. Okay, yep. I will explain what it is in a moment. So I knew about that concept. Not all of you do yet, but you will soon. And then I said, well, if you have debt, then you can get bankruptcy, can't you? And so I thought maybe the way our system had stopped being changeable, that was actually bankruptcy. You had to throw away the system. And there's another problem, because even though we were using Agile and everything, our shareholder wasn't that keen on the software's never done concept, and that's sort of the way we set things up. So that was another one to explain. But I guess I won't go into every single aspect. We're an Agile company. We use Kanban. That was mentioned earlier, I think, by Adrian. That means our stories are intended to take less than a week before they get delivered to customers. We deploy about 60 times a week our application or suite of applications. We use continuous delivery. I'm not going to talk about any of that. It's irrelevant to my point here. Although the fix is relevant to that. So our old system, it took about a week for a rating change. Rating changes, I want to charge someone a little bit more, I want to charge someone a little bit less for their particular risk. They work at heights 10 meters. We want to add on 10% onto their premium because of that. That's the kind of change. In the new system, that's able to be done by a non-technical person into our code. So they commit code into our code base, and it takes them an hour to deploy it. So that's the benefit, but yeah, it took us a long time, and the old system is not dead yet. So on to my conclusions. I'm going to start with the back at the front and that kind of thing, because that's the kind of person I am. And I want you as confused as possible by the time I get to the equations. So I think the actual bankruptcy of organizations is probably quite high, coming on the back of technical bankruptcy of their systems. So not much reported in the news, so a little bit hard to identify. But when you think about the impact of a system that no longer fits the needs of your business and cannot be changed as your business changes, your organization changes, whatever it is, that's a recipe for the end. Not always. Maybe you have time to rewrite it, but a few of the examples. Friendster. I remember that at a certain point it was taking me 40 seconds to log on to this social network that pretty much looked like Facebook. And I was just not interested in waiting 40 seconds to find out what someone had for breakfast or what their cats looked like. Which, by the way, everyone at the office said, I need to put more cats in this presentation. I didn't do it. I apologize. I know. Very bad presenter. The video management system at BBC, which I think you all heard about potentially in the news, very high profile, canceled, gone, dead, and I think so was the person who was responsible for it, and maybe everyone else responsible for it. A new air traffic control system in the US that never got flying, as it were, and the National Program for IT, which was a healthcare program that was, I guess the software itself was going to cost $6 million. Probably everyone in this room worked on it because I think it employed everyone in the country. And I think the total cost would have been $12 million. I think it's just dead, gone. And, you know, started badly and ended badly, I suppose is the best way to look at it. So yeah, I've created some equations to help us reason about how much debt, technical-wise, we're accumulating in our system, and how we might pay it off, or are we paying it off, and what is the damage that it causes. And really, the way I want to look at it is, what is the amount of effort it takes to add one more unit of complexity? And I'll talk about complexity. So, you know, typically I would think of a line of code. How much effort is it going to take me to just put a little bit more into my system? And I'm looking at software. But before I just talk about software, I think the same behaviors exist in businesses and in organizations. So some examples of things not done properly. The signal failures on the London Tube, that's debt that we're paying off from, I don't know, people that put it in place long before I was in this country. The railways in general, someone on the train said, yeah, sure, you can't get internet on the train today, but at least it's on time. And I thought, that's a good example. At Simply Business, we have toilets that don't flush very well. Doesn't matter how many times the plumber comes out, they still don't flush very well. But, you know, bridges that have not been repaired for earthquakes are just too expensive to replace. Strikes are a sign of your organization not being in a very good state. Obviously, people are not happy. And then actual bankruptcy. You know, the Iraqi army is clearly an organization that isn't working well. It's not defeating IS, even though we and my country, your country, etc., have poured billions of dollars into that. The garment factory that collapsed in Bangladesh, worldwide corruption, all of these things fall into the same example of behaviors. And I'm hoping you'll see my analogy of technology and software in other domains, for those of you that are not technology and software. Stephen reminded me that not everyone here is a developer or former developer. So I will catch everything as software. I'll leave it to you to transfer it to your domain. That was the last time I'm going to do that, because my previous iteration of this presentation, they said, you keep talking about all the different things, and that confused us even more than the equations. And I said, okay, fine. And then I will give you some hints at the end to think about how to deal with tech debt. How am I doing on time? It's going to be tough. All right, so some definitions. This is when you start raising your hand if it doesn't make sense. So tech bankruptcy. What is tech bankruptcy? So the definition is relatively simple, although it is also relative. The economic time or cost of making a change to a system exceeds the needed return from that change. So basically, it's not worth making the change. And that change could be as simple as replacing that broken chair right over there. It's just not worth changing it. We're going to leave it. Or it's something much greater, an enrollment system, whatever, in the university. However, the system may be working and stable. So the system may function, and this was the case with our system. We could sell policies. We continued to sell policies. We just couldn't innovate our business. We couldn't grow the business in the way we wanted to with that system. And I suppose implicit in all of this is things are changing. And I said the software was never done. The system's never done. The highways are never done. I think the Golden Gate Bridge in San Francisco, where I spent 10 years, the Golden Gate Bridge, they paint the whole thing to make sure it doesn't corrode. And as soon as they get to the end, they start at the beginning again. They're always, always, always painting. And I think software ends up being a lot like that. And a lot of systems end up being a lot like that. The world changes. So what is the problem with tech bankruptcy? I guess it's fairly obvious, but there's a few other subtleties. It's usually recognized long after the bankruptcy occurred. You find out you didn't fix your roof on your house in time when the whole house floods during the winter storms. It's too late. That's too late. You can't fix it. Or you can't floss your teeth when you're getting a root canal to fix the root canal. It's just too late, right? It's all happened. It's in the past. Or any other thing and then businesses, I do believe, fail because of it. Because it's just too slow. So I imagine at some certain point, Friendster, for example, noticed that no one was coming back to their site anymore. Not the number of daily users was probably just plummeting, and they said, oh well, now let's get those servers. The CFO probably said, do you know what? Let's get those servers in as quickly as possible. Let's reduce those bottlenecks. Let's make the site perform quicker. And by the way, it did, because no one was going anymore, so it started performing quicker and quicker, I imagine. I wasn't there, but that's what I think happened. But it was too late. The customers were gone. So moving on. So the definition of technical debt, the next definition. Did everyone get technical bankruptcy? Does it make sense? Yeah? Hands up? I see nods. Okay. Whew. Okay, first job done. So the definition of technical debt is very simple as well, in theory. The work that has not been done. So any work that you should have done to get the benefit, whether it's benefit or feature or whatever you want to call it, that work which you didn't do and you probably knew you should have, or whoever should have, that's the technical debt. So really it's, more formally, it's the difference between doing something properly and the less correct way it was actually done. And I think every single one of us can think of the less correct ways a lot of things were done, right? And I'm going to try to quantify how badly that less correctedness thing was. So yeah, you can quantify it sort of by the amount of work left to correct the implementation versus the effort of the original implementation. So I'm going to talk about the ratio of technical debt to the overall solution, the overall complexity of the solution. And just to be clear, this is not an excuse for saying I have to build the Taj Mahal just to get a building, or it's not about gold plating everything. It's about things you actually needed in order to get something done. If you build a customer management system and you didn't build the ability to change someone's email, that's technical debt. And by the way, we did that, shockingly. And now we're fixing it. So what's the problem with technical debt? It makes good solutions bad, very simply. It increases the cost of making changes. That's where the equation will come in. And it starts slowly and picks up speed. So you don't see it, you don't know it's coming. You kind of know it might be a bit of a problem. Turns out it's a much bigger problem than you ever thought. Equation will try to prove that as well. Actually, the equation, there's some caveats, but and eventually tech bankruptcy arrives, and it is too late. It is just too late. There's nothing you can do. That's the definition of it. So there's a bit of intuition about tech debt. I suppose this is sort of, you all know this, right? You have to pay debt off, at least if you went to university or whatever. The principal needs to be paid off. The interest accrues. How fast? So this is 10% interest accruing over a 30-year period on what looks like a quite small principal if you're not paying anything off. So you can see that the debt overwhelms in an exponential form if you're not paying things off. So yeah, I was trying to answer the question, how fast does this happen? How bad is it? Obviously, if you're getting wealthy at the same pace, no problems. But so I had to go one more thing, which was, I talked a bit about complexity already. Oh, so sorry, does everyone get what technical debt is? Raise your hands. Okay, moving along swiftly. So complexity is really what you choose it to be, but it's kind of a quantification, a breaking down of your big thing into something smaller. So a unit of the final product, in development software, lines of code, rows in a database, function points, and for the purposes of what I'm going to show you, you can choose one or all of them, combine them, create some really fancy equation to decide what your complexity is. I don't care. Do what you want. In terms of businesses and organizations, sorry, I am going to mention the alternate universe here for a second. Employees is a really good one. Paragraphs in laws, customers, all of those are complexity that affect your system. And I think it was interesting, we talked a bit about in a few of the earlier talks, I think Adrian, you were talking about the complexity of changing the organization to adopt Agile, right? Well, that's the same as the complexity of changing your code to add customer details, right? The problems are the same. organizational change. You mentioned software projects fail at 68% rate. Well, it turns out organizational change projects fail at a 70% rate. Very similar. And now, there are some things I won't go into, but there's some implications of the equation I'm going to show you that might lead you to think command and control might be a good idea in organizations. But I don't agree with that. So, just a caveat. These are hypotheses. This is thinking I've been doing mostly inside here, and there's some backup, some data, but I'm kind of floating an idea here. This is hopefully original thinking or slightly original thinking, and hopefully useful. But it is based on the nature of mathematical equations, the empirical information. It's primarily, though, a thought experiment, and further investigation would be warranted. So debt and complexity are the two angles. These are my two angles, a little bit less meme-based angles. Apologies for that. So complexity is kind of the base. The more complex your thing, your organization, whatever it is, that should affect how hard it is to make change, if that makes sense, right? So if I have more lines of code, when I add that next line of code, there's a possibility that there's more places I need to make sure that line of code works. So that's part one. And then debt is the accelerant. It's the jet fuel that you put on the cost of making change. That's the way it looks. Makes things worse. So I looked at the evidence beyond simply business. So I had seen technical debt, and I've been around the block a few times as well. So debt makes good code bad. What does bad look like? And so this is a focus on maintenance, which is not the same as adding or changing, but maintenance is one aspect of change that you need to manage. So generally smaller changes, overall maintenance. And this is someone named Capers-Jones from the Software Productivity Institute, or he may have changed his organizations a few times, who did research on this, and there's a link there which is available. So a leading piece of software will have excellent quality control. And by the way, the defense industry is apparently the source of most of these types of projects where there's very strict requirements, etc. But these they have excellent quality control, very good code structure, 0 error-prone modules. So an error-prone module would be a module that has a lot of errors versus the overall quality level of the application. And very low bad fix injection rate of 1% or less. What that means is when a problem occurs, the fix doesn't cause another problem. So if every time you fix something, you get another problem, that would be 100% bad fix injection rate, I believe at least. So the interesting thing, this kind of a project, this kind of software, the maintenance costs decline every year. They become less and less over a 5-year ownership period. Unlike the average one, where there's marginal quality control, reasonable initial code structure, 1 or 2 error-prone modules. Not that many, 1 or 2, right? There might be 100 modules in one of these things. The bad fix injection rate goes up to 7%. This might be where I drink some water before I have a technical bankruptcy of my throat. Sparkling, not what I expected. The maintenance costs, in this case, increase over a 5-year period, but not at a very significant rate. So you would see that the number of people you have maintaining your code won't be going down, but it might be staying flat. So if you're adding new features, you might be able to stick, if you're growing the team, you're going to get most of the benefit on new features. Lagging. This is the bad one. Inadequate quality control, poor code structure, up to a dozen severe error-prone modules, and bad injection rate of 20%. What happens in this case is you rapidly approach bankruptcy. So maintenance costs become more expensive every year due to entropy, and the application never stabilizes. So what happens is that in the lagging scenario, you actually get a negative ROI in 3 to 5 years. What that means is you have to throw it out. It's no longer valuable in 3 to 5 years. And we've probably all seen systems like that where they either should have been thrown out or they have been thrown out. That happened to us. That's tech bankruptcy. The interesting thing is how different it is from the leading scenario. How an exponential difference, right? The leading scenario, you could get 20 to 30 years of positive ROI. I looked at some other numbers where the difference between doing it badly and doing it well was 55 times, right? Those are all exponential numbers. You're going to see some exponential numbers when it comes to debt in a minute. So I want to quantify the two parts of my equation, the complexity of the system, and we need to choose an equation for complexity, how much harder it is in a perfect system to add a line of code, and then how much worse it gets when you get technical debt. So we're looking, the specific thing we'll look at is what is the level of effort on a relative basis to add 1 unit of complexity to my system. How many people are following me so far? Raise your hands. Okay, does anyone want to ask a question? Because there's a few of you that were going, well, I'm not so sure. Okay, sorry, then I can't help you, but hopefully it will come to fruition. So let's look at complexity measures. So there's some options around which measures I could use. So the complexity measure of adding a line of code, adding an employee, whatever, is based on not just writing that particular line of code based on the feature that you have, but then also where else that affects, right? So you think about it intuitively, it's write tests, write line of code, change all the other places that either depend or are affected by that line of code. So if my line of code needs to access a variable over here or a feature over there, then it makes a call to that thing. And if that thing is not returning the right thing, make a change over there, etc. So there's some interconnectedness, right? It's part of a system. Or if you're introducing a new employee, you need to train them and introduce them to their colleagues, right? And then you repeat that until all that has done and the thing you want is embedded. So we're looking for the best case scenario in this case. And when I talk about complexity from now on, I'm going to use the word N, the letter N. So N will be the number, that's how you keep it in your head, number of complexities or things, whatever. Does it make sense? N, everyone's got N? Yes? Okay, we can agree on that. So here's the graph. So there's a few variations here. If you think about the bottom line, that's log n. So even as you go from 0 to 100 complexity units, the amount of effort to add a new line of code doesn't go up very much. The natural logarithm of n is n. But then you could go to the next level where n, where basically every line of code makes it that much harder to add another line of code. And then you get to n log n, and now that actually goes much more quickly. So you've got and by the way, these are the properties of a number of algorithms that are out there, and that's why these numbers are interesting. So for example, sorting is an n log n problem if you use a good algorithm, whereas searching is a log n algorithm if you use a good algorithm. Searching if you use a bad algorithm is n. So, and then n squared, where everything interacts with everything else, you can see that the effort starts just shooting off the roof. If you added your first 20 lines of code, that cost you 300. Adding the next 20 lines of code, you won't be able to afford it, will you? Certainly not based on if you budgeted with that first cost. So those are some options. I want to talk really briefly about Metcalfe's law. How much time do I have still? 10 minutes?
No, 20.
20. Okay. So Metcalfe's law, and now I'm starting to stretch some metaphors to try to explain to you how I came up with my equation. So Metcalfe's law was all about saying that the value of a network, say Facebook or the internet or the telephone network in this case, increases based on the number of nodes that are connected. And he said it increases by the square of the connections. Those little black lines are the connections. And he looked at every connection going one way and back. So the phone on the left can call the phone on the right at the top, and the phone on the right can call the phone on the left. That's 2 values. And so when you start adding 5 phones, you've got 5 squared, so 25 connections, and that's much more valuable. Now, that seems really positive, right? However, if you're writing your code, and for every single phone connection, you need to basically drag a wire between the phones, then the cost of that network will go up at the same rate as the value of the network. And so that network down there below goes up in cost extremely quickly, right? Which is why it wasn't built that way. So our phone network it interconnects everything, but actually each phone connects into one thing. And I'll show you some other diagrams that look more like a real phone network.
Can I ask, if it's squared, how come you not got 25 lines on the second diagram?
So it's actually n times n minus 1, and there's also the multiple directions, but it's roughly squared is the best way to put it.
How many lines have we actually got?
So it's bidirectional.
Yeah.
So basically...
10 lines, 20 connections.
Just 10 lines, yeah, it's 20
10 lines,
connections.
20 connections.
Yeah. So you've got 5 times
Which
2.
is 5 times 4.
Yeah.
So I'm not going to try to go back and think through all the math, but the main point is that it's basically n times n minus 1 connections from each connection. That makes sense? And then you get sort of the opposite of that, and it comes back around. So the math is a little bit more complicated, but it's definitely on the order of n squared. So you're absolutely right, and thank you for calling me on that. I took that out on the advice of people on my team going, it's a little too complicated and it's not quite your point. So the point is, the more it connects up, the more expensive it gets. The binary tree, and again, you can argue, the main thing about a binary tree, and this is a stretch in the other direction, is there's very few interconnections. So this tree actually has roughly the same number of nodes as the interconnected one. I'll show you the difference. But the number of connections actually increase more like the log of n, right? So each thing is connected to one other thing or 2 other things, and the log of n is actually the number of rows in this table. So there's 16 items on the bottom. There are 4 rows in the table because the log 2, for the accurate people, of 16 is 4. And so the natural logarithm grows at a much more slow rate. So if you add another node over here on the left, you're not going to have to change the whole tree, that whole interconnected network, right? So it turns out a huge amount of work has gone on in software to compartmentalize code, to have small changes have small effects. And that's, so things like object-oriented programming, patterns, functions, and in other domains, methodologies for executing organizational change, how to run companies more effectively. And all of these are intended to allow us to build larger organizations and bigger code bases. So compartmentalization is really important. Otherwise, you get systemic effects, meaning something over here affects something over there. So, traffic on the M25, that's a systemic effect if that affects traffic on Regent Street in London or traffic over here, which we do see that happen, right? We have systemic effects all the time. That means those things are actually connected together. We do a lot of work to unconnect things in software. So I've gone with the best case scenario, which is that it's log n. So good code, good organizations, or good whatever, meaning easy to change, their complexity increases at the rate of log n. So slower, you can add people, you can add lines of code, you can just grow this thing without really worrying about it too much. Your cost to add each single thing will not go up, or not go up very much. And only occasionally will it have a wider reaching effect. So that's where that extra cost So the average case is probably that it remains flat, and then there's occasionally when you have to do a big piece of work. So this is what log n actually looks like up there on the left. So you can see how it flattens out. We saw another graph showing it being totally flat. Right at the beginning it goes up, and then it just flattens right out. Everyone following or pseudo-following? Raise your hand if you're more or less following. Hey, I'm feeling pretty lucky. So there we go. So there's the two connections, right? You can see there's a lot fewer connections here, even if I didn't get my maths entirely right. There's a lot fewer connections. If you thought of all those things on the left, my drawing skills, etc., were not good enough to make lots of telephones on the left. No, that's a lie. I just didn't do it. So let's go into technical debt. Back to the acid or the fuel, the jet fuel. So technical debt in complexity terms, it takes the log n of good code, which is that blue line at the bottom, and it makes it worse. It makes it worse in one of these forms. If that makes sense, yeah? So does it accumulate quickly? So in theory, you'd say technical debt's not that big a problem. I know we've done some things not that well, whatever, it'll be fine. We'll fix it when we need to, right? There's not really a rush. There's sort of two problems, which is that, yeah, it's the brushing your teeth, flossing, right? You don't know your teeth are going to fall out until they fall out. You just know that you should have flossed. At that point, you're going to go, I wish I just flossed a lot more. But it's too late. It also accumulates silently. So the slowdown, in our case, the slowdown you'll see as you're developing code will be gradual. And in fact, if you're introducing a lot of technical debt, it will feel like you're going really quickly because you're not doing all the work you should be doing. So you can reinforce yourself to think, look how quick I am. Look, we've just added this other feature and this other feature and this other feature, while you're leaving behind a wake of stuff you didn't do, things you needed to do. And so it's kind of a silent killer. And the acceleration then, as you saw, exponential acceleration isn't a gentle, it starts slowly. It's like one of those, they call them dead man's curves, right? Where the I think it's the arc of the curve, I forget what the term is, but I guess the derivative of the curve starts getting higher and higher, right? Your curve just starts, that's where people crash their cars. They don't realize that the curve is getting tighter and tighter, and so they assume that the curve will stay flat. That's, I think, what happens here as well. We don't think in exponents. There's another reason why it accumulates quickly, which is that decisions get made at multiple levels. Decisions to drop features. You might think you're entirely in control, and you're not. We talked a lot about other things. I think you were talking about things outside, and you were as well, about things affecting other things, and I think that's true here. But this is just inside a small microcosm. So management decides to defer a feature, says, let's increase speed. We need to get this out. We've got a budget to hit. We need to get this out. We'll not build that other bit. It's not that important, is it? And then the team still has a tough deadline to hit, and they go, why don't we at the lower level also cut some of the functionality of the features that the management team said we're going to get? So what happens when you do this? You get a multiplier effect. So if we look at the top thing, 10% of the scope was cut by management, meaning 90% was done right. The team cut 10% as well. By the way, this is a very, very good case, right? This is people doing 90% right. That's pretty good. Who does 90% of their project right? Not very many people, actually, it turns out. Then you multiply the things done right together, you got 0.81, meaning you increased your debt by 19. You have a 19% debt rate, right? So you're actually going to have to pay off twice what any one of those people thought they were going to have to pay off. And if you get to 30%, which still seems pretty good, 30%, we did most of it. 70% of our stuff is done right, and we can pay that other bit off in the the 30% months, the last 2 months of the year or whatever it is, when we're going to pay everything off, which never come. So you do that, you got 50% of your system built. 50%. You're gonna have to. It's not just the last few months of the year. it's the whole next year is going to be paying off this year. You do that 2-3 years, so you do that for 3 years, you'll have 3 years of payoff. That's going to be bankruptcy. That's going to be tech bankruptcy. And yeah, if you go down to 50%, if you're at that point, you probably never get the thing live in the first place, right? There's no chance, really. So I put the equation together. It's the log n of good complexity, good code, and then 1 over 1 minus the debt. Let me explain what that looks like. So 1 over 1 minus the debt is really 1 over the goodness, right? 1 minus the debt, if you say the debt is 30%, then the goodness is 70%. 1 minus 30% is 70%. And then you use that as an exponent. So you divide. Basically, if it's all good, that number is 1 over 1. If it's all bad, that number is infinite, and you get log n to the infinite. Of course, not really easy to get to that. But, and somewhere in between, you get squared, right? So if your debt is 50%, you're going to take your log n and square it. Does that make sense? Yeah? So here's the graph. For different debt ratios, so the bottom one, which you can barely see the light pale color, is, so we've got 3. It looks like the 0 one is actually, so the 0 one actually is cruising along at the bottom. You can't even see it because there's no debt, and the log n. Then you see 0.1 over at the 10. I don't know where the 0th line went, by the way. Apologies for that. You can see that as your debt ratio just increases to 0.3, from 0.1, the level of effort, which is on the left, with the complexity on the bottom, the level of effort to make changes, 1 unit of change, triples. And this is early on in the progression, right? So you get a lot of impact. Interestingly as well, the level of complexity overall has very little impact. So here's another way of looking at debt versus lines of code. So here we've talked about complexity. The bottom line is 1,000 complexity. The middle line is 10,000, and the top is 100,000. And as you can see, as the debt goes up, the impact of the size goes up as well. So the debt gets worse at the same amount of debt. That's obviously more lines of code that are in debt. But the impact of that on your overall effort goes up more, disproportionately, based on the complexity. Does that make sense? This one's a little bit, took me a while to get my head around. Raise your hand if that more or less makes sense. Okay, so we're at 70%. By the end, no one will be raising their hand, I'm worried. That's probably my nightmare. Yeah, was there a question?
Just wondering if you had any data that indicated that this is true, or this is just possibility.
So there's postulation side of it, but I think if we looked at that lagging versus the best case scenario, you see a very exponential effect, and also when you just experience of coding. So definitely there's a level of testing this out. Are these the right numbers, etc. So it's not empirically proven. Let's put it that way. There's certainly an exponential aspect to doing it badly, though. And I think, when we see projects that fail, they fail really badly, right? It's not, I think a lot of people think of projects in general where they think the equation of project done well, or average project, if that's a flat line, project done well, the delivery is a little bit faster, and project done badly is a little bit worse. But the actual reality is that project done badly never gets delivered at all, and project done well gets delivered a lot better than project done average. And I think so. I think there's an exponential thing, but it's definitely a valid question, or something that is an action for you guys to take as you think about it. And finally, if this is true, then if you look at productivity, this is what happens to your productivity as your debt increases. So as you get to 0.8 debt, you're pretty much at 0 productivity. You're not delivering anything. But even at 0.1 debt, you've already lost 20% of your, or actually more than 20% of your productivity. And at 0.2, you're getting down to 50%-ish of your overall productivity using this equation that isn't proven. But again, I think this does ring true. And by the way, I say it's not empirically proven. I looked at quite a lot of other equations and algorithms and looked at their properties, and they just didn't make sense. They didn't behave in that way. There wasn't enough exponential. The exponential here is much greater than I expected in some ways, and the effective complexity is much lower than I expected. But none of the other equations really rang true. It definitely doesn't take the complexity of adding one unit to your software doesn't go up by n when isn't n based when you add one. It's definitely less, and the complexity of debt is definitely greater than n. So next steps: investigation to prove the equations are right, as was well spotted, and I think the other side is better ways to measure debt and complexity. I think, I've taken a very basic approach. I've said your complexity is the lines of code, but, it could be lines of code times 1.2 times the rows in the database, et cetera, et cetera. There's a lot of different ways that you could say, well, what is my complexity? And the same for what is my level of debt. To say there's 30% debt, well, what is debt? How do you measure that on an ongoing basis? Do you measure the debt in every project? That might be a bit tricky. We talked about not getting too hung up. And I would say, don't get too hung up in these things, because understanding if your debt is 0.1 or 0.8 is going to be far more valuable than if it's 0.1 or 0.101. The accuracy isn't going to help you, but and mostly this is also a communication mechanism for people that want to cut corners. So what can you do? If you aren't scared yet, get scared. So who's not scared yet? A few people aren't scared yet. Everyone else is scared. Raise your hand if you're scared. Okay, so 50% scared. So the rest of you get scared, please. Otherwise, the symptoms. So what are the symptoms? Well, are you leading, average, or lagging? I think that's pretty easy to see. And if you think of lagging, that looked like it might be, 50% debt level, maybe it's a 40% debt level. Leading was, 0 to 5% debt level, which I'm not sure I've ever seen, to be honest, in my career. It's pretty rare. I think that debt levels are, in the 10 to 20 to 30% range for most systems we see out there. So where do you stand in that? Are you leading, average, or lagging with your projects? And then you can start to see, well, is this thing going to be around for very long? Should I be looking for another job or something like that? Hopefully you can start to fix it. I believe that the differences are easily visible. They certainly have been in my career. The debt ratio needs to be low, but yeah, you don't need to know it exactly. And finally, do things properly. It turns out that the techniques to do things properly are fairly well established, just the quantification of the impact of them. So things like peer reviews, formal controls, good structure, a lot of things that we preach in Agile, right? When, it was interesting, I think you mentioned doing the design phase in Agile and then handing it over for the delivery phase. And the delivery phase didn't go so well, right? Because it wasn't in Agile. Agile's one of the things it talks about is it's done when the code is done, when it's live, when it's in front of customers. That's when it's done, not in the phases before that, right? And part of what finds your bugs is your customers, is it being used live, and things like that. So a lot of those things, test-driven development, all of those things are things you can do properly. In organizations, I suppose, going into other areas or in construction, I think it's still about doing it properly. Make sure your employees know their jobs, right? Make sure that, I think the video showed as well was quite interesting, right? We think about, you have to basically, if you think back to interconnections, right? If you have to talk to every part of the business and negotiate with 50 different stakeholders to do your project, you've got your tech debt in the organization, don't you? Exactly. You're sitting there, you look like you've built the network in every single person, and there's no way for you to do your project, right? And one of the things that we do in our projects is we have a lot of stakeholders in our projects, and we see two effects. One is if the stakeholders aren't properly engaged, then the project feels like designed by committee. I need to go to this person, get their buy-in, then I go to this person, get their buy-in, and then they come back, and then it turns out that's not right for them. And that's people not being properly engaged. When we have people engaged, even if it's the same size team and everyone's working together, then the project goes really quickly because you have all the right people. And I think that this, to me, going through this exercise made me think about software development in a profoundly different way, and that sort of deepened my understanding of why it is that object orientation is important, why it is that encapsulation is important, and that the real corrosion in your software is the interconnection between all of the different things and the way it locks you into concrete so you can't move anything. So that's really, now, interestingly, if you want things not to be changeable, you know what to do now, right? Connect them up, right? If you want a system, part of your system never to change, like say your culture, or you might really connect that up. Make sure everyone's talking to everyone about culture. You won't be able to change it after that, and that might be a really good thing. Those are those are very, very small, long list of estimates. I don't know how we got the extra space in there. That was Keynote switching to PowerPoint for me. But these are all some random, some not so random things that I drew on to work on this, plus my own experience. And yeah, questions. Actually, one question from me first. Now, how many of you followed it? Roughly, raise your hand. Okay, so 70%. Well, thank you very much for your attention. And like I said, any questions?